Welcome. This is Module 5. In this lecture, I'm going to try to provide an understanding about the relationship between abnormalities seen on visual fields with static automated perimetry and damage as seen on OCT. Now, probably this is the lecture that has the most information that is new, at least for many of you. So you may want to listen to this lecture more than once if you can bear it. Alternatively, or in addition, this is a reference to a review article that was published about a year ago that covers a lot of the material that's in this particular module. So first of all, why is it important to have a deep understanding of the relationship between visual fields and OCT? Well, I return to the definition of glaucoma and the fact there's no litmus test for glaucoma, that it's a progressive optic neuropathy that's characterized by a specific pattern of anatomical, in this case we're going to mean OCT, and behavioral, in this case we're going to mean visual field changes. So it's important to understand, because of this, how the patterns of damage seen on visual fields are related to the patterns of damage on the OCT. Okay, so first review of retinal locations of visual field points. So here's our model with the 24-2 points superimposed. If we put them on these points on top of the fundus photo, we see this representation here on the right. Here's our model superimposed upon this. And here is the macula schematic model with the 10-2 points superimposed. We can add those now, and now we have a fundus view with both the 24-2 points and the 10-2 points. And there's the so-called macular region, right? And I'll remind you that these points are morphed here because we're taking into consideration that light falling, let's say here in the fovea, is really stimulating ganglion cells out there. And for that purpose, we make use of corrections that can be found in Drasdo et al. From Christine Curcio's lab. All right, so in addition to the 24-2, the clinician has at his or her disposal the 10-2 Humphrey field. And let me just remind you or tell you, as the case may be, that this visual field starts out, this visual field has points that are heavily concentrated in the macula because they're spaced every 2 degrees, starting up and over by 1 degree. So there are the 10-2 points. This would be superior retina or inferior visual field. This would be inferior retina or superior visual field because, as you know, the superior retina corresponds to an inferior visual field and vice versa. So this arrow here in the visual field would look like this. Or, more to the point, the image that you're looking at the moment is a tiny little image, is represented on the back of the eye with a tiny little image of light, and it's inverted. Now it's inverted superior and inferiorly, but not nasal and temporal. So an arrow appearing in the visual field like this would appear as so on the back of your eye. All right, now, where is the damage as seen on OCT? Where do we expect circumpapillary retinal nerve fiber damage due to glaucoma? Well, we start out with these vulnerable zones with the traditional view that the superior and inferior quadrants here of the disc are particularly vulnerable to glaucomatous damage. And in a study in 2013, we asked whether we could say something a little more than that. So here's some data from that study. Here is retinal nerve fiber layer thickness for some healthy control eyes. So blue is thinner retinal nerve fiber layer, red is thicker retinal nerve fiber layer. Here are the average results for a group of patients with moderate loss as defined by the 24-2 mean deviation. And to get a feel for what is lost due to moderate glaucoma, we're going to subtract this from this and get this plot. But now red means something different. This is now a thinning plot, but it's like the probability plots you see. Green means not thinner than normal, and dark red means much thinner than normal. So let's blow this up. Extensive thinning of the retinal nerve fiber layer in these patients with moderate loss within normal limits. All right. Notice that to a first approximation, it's not the entire superior and inferior quadrants that are most affected. It's the temporal half of each, as shown by the orange and green arcs. So let's take this now and move it over here. So there's the inferior region that's vulnerable, and there's the superior region, and that's the retinal nerve fiber layer thinning. Okay, so where do we expect circumpapillary damage due to glaucoma? Well, we expect it here, and we expect it here. All right, so in a recent paper, we referred to these as the superior vulnerability zone and the inferior vulnerability zone. Okay, where do we expect macular retinal ganglion cell damage due to glaucoma? Well, let's go back to our schematic map of the macula. And I'll remind you what by macular I mean that portion of the retina that around fixation plus or minus 8 degrees, that while it only includes 2% of the retina, has over 30% of the ganglion cells. So here's the macular model now. It stretches from here to here. And notice this overlap region. Notice the macula overlaps with the inferior vulnerability zone, and this is what we've called the macular vulnerability zone. And as I'll emphasize in a moment, early glaucoma is often present in the macular vulnerability zone, and it can be missed and or underestimated with a 24-2 visual field, and even with disc scans in some cases. I'll return to that point. Okay, so this answered the question, what regions of the disc are most affected by glaucoma? Now let's change that to what regions of the macula are most vulnerable to glaucoma, and how does it relate to the disc? All right, so let's replace retinal nerve fiber layer with retinal ganglion cell thickness for the controls. Age-matched patients with moderate glaucoma. There's the ganglion cell thickness curve. Again, let's subtract this from this. And now this is a difference curve. Let's blow it up. Dark red means a lot of thinning of the retinal ganglion cell. Green means very little thinning. So let's take this and move it over here to the fundus. And so now we have retinal ganglion cell loss and retinal nerve fiber layer loss. The important point I want to emphasize here is ganglion cells in this very vulnerable region here, they send their axons right smack into the most vulnerable part of the disc, right? That's the reason for the macular vulnerability zone. Or actually, that's the reason for the loss in the inferior macula here. It's because those axons are going right into the macular vulnerability zone. Okay, so this summarizes it. This circle represents the edge of the macula as I define it, plus or minus 8 degrees. This is from the thinning from the patients with mean deviations that are classified as moderate. That's where the most damage is. This region here that's less vulnerable sends their axons into the temporal zone, by and large, or temporal quadrant, right? The axons up here, the ganglion cells up here send their axons into the superior quadrant. This is your classic superior arcuate or inferior arcuate on the visual field. And this is also your classic arcuate, so that's very vulnerable. However, this region here also is vulnerable because it too sends its axons into this inferior region. And this overlap between the macular projection and the inferior vulnerability zone is what we call the macular vulnerability zone. So this region is less vulnerable, that region is more vulnerable, and then the regions just outside here are more vulnerable. Okay, what do we know about the location of damage in early glaucoma? Well, how common is it? So here's 57 eyes from that same study I described in Module 4. They all had early glaucoma, early being defined here not by how deep a defect might be near fixation, but simply based on the classic definition of the 24-2 mean deviation being better than -6 dB. These were judged by 2 glaucoma specialists based on OCT, 24-2, 10-2 visual fields, stereo photos, IOP history. These 2 clinicians who were not involved in the patient care had all this information. 34 of these eyes, or 60%, that were judged as having early glaucoma, right, had damage in the superior vulnerability zone. Over 80%, or 46 eyes, had damage in the inferior vulnerability zone. Right? So 55 of the 50, so there's a lot of overlap here. Some eyes had both, right? Overall, all but 2 of the eyes had clear damage in either the superior vulnerability zone or the inferior vulnerability zone, as indicated by retinal nerve fibrillary thinning dipping into the red on the retinal nerve fibrillary scans. Right? The other 2 actually were borderline. So essentially, all these eyes had damage in the superior and or inferior vulnerability zones. Again, this is the macular vulnerability zone here. 44 eyes had damage in that region. And then if you include this region here, which often has diffuse damage or in some cases local damage here, you wind up with, in this particular group, something like 88% had macular damage in early glaucoma. Now it's going to depend. We may have had a few more normal tension than in standard clinical practice, so these percentages will change a little bit. But damage to the macula is common, and it often includes the macular vulnerability zone. All right, so what's the implications for visual fields? Well, here's the 24-2 again. And again, I want to remind you, it's the most common visual field test used to diagnose glaucoma. It's got a 6-degree grid. So where should we expect visual field damage on this? So the visual fields are often categorized based on patterns of glaucomatous damage, and there are different schemes out there. Here's one that from Keltner, Johnson, and colleagues that was used in the Oates trial. And I took I modified that figure a little bit to represent all these defects as upper visual field defects. And so here's a nasal step. I believe that classification of a nasal step required, 3 or so of the points here to be abnormal. Here's paracentral defect, a couple points here crossing the midline. Here is a partial arcuate, which now has clear damage in both quadrants, but it may not completely connect with the blind spot. Here's arcuate damage, and then altitudinal. Now, where should we expect visual field damage? Well, here's a map. Here's our map that relates the location of 24-2 fields to the locations on the retina for an average eye, right? By the way, this is a 30-2, so it's got an extra ring of points. All right, so let's combine it with our model of where damage is, right? So the implication of this combination is that these defects here are all related to damage in this region here and damage in this region here. In fact, in most cases, because of this starts up and over 3 degrees, most cases they're related to damage in this region here. That's only 45 or maybe 60 degrees wide. So let's put this model on. We have to flip it, of course, because the image is flipped. And there it is. And there it is. So you can see the damage here all falling in this region as expected. What about the altitudinal? Well, all of this damage would be related to what's happening in here. And the damage outside, of course, would be around onto the nasal side. Okay, so to repeat, all of these upper visual field defects are largely due to damage in a 45 degree to 90 degree wide region of the disc. Most of it's right in here. And it includes the macular vulnerability zone. Okay. So, I've already argued and supplied evidence that macular damage can be missed or underestimated on the 24-2 visual field test. And the reason for that, I'll remind you, is that the damage here, right, is poorly sampled by the 24-2. So this is the most damaged region, and here are your points. You've got these 2 points that are close to it, but not even on it. So it's not surprising that the 24-2 can miss, right? Completely miss in some cases, and underestimate in most cases macular damage. So here's an eye that's not atypical, in which the 24-2 and 10-2 visual fields were obtained on the same day. And just to remind you, that's what the retinal ganglions, that's the macula is plus or minus 8 degrees, and it represents the densest region of retinal ganglion cells. So let's put this 8-degree circle here, so the other 4 points in here. So since this is starting up and over 6, because these are spaced every 6 degrees, and they're starting up and over at 3 degrees in fixation, you only have 2 here within this region. Because these 10-2 points are spaced every 2 degrees now, and start up and over 1 degree, you've got all of these points now in this same region. So, here's a defect. Where is it there? Well, to understand what's happening, or to show you what's happening, let's take these 24-2 points, scale them up and put them on here, and then let's outline where the deep part of this defect is. You see it's falling between the points on the 24-2. If we scale this to size and put it back here, you see it's a small defect that falls right in between these points. Right? Now, a number of studies have documented that the 24-2 can miss or underestimate macular damage, and I list a couple of them here. All right. So, clinical implications. Early glaucomatous damage of the macula is common. It's often an arcuate-like defect close to fixation in the upper visual field. But this damage can be diffuse and widespread as well, as I'll mention later. It's missed or underestimated with a field test with a 6-degree grid. So as a clinician, you've got a couple of choices here. The clinicians I work most closely with now routinely perform a 10-2. In some cases on every patient, if not on the first visit, the second visit. At the very least, you want to perform a 10-2 if there's any indication in the patient's history or any hint on the 24-2 of an abnormality. So one funny point on the 24-2 in the center, a complaint about glare, an acuity that isn't 20/20, anything at all should buy you a 10-2 if you're not doing it routinely on everyone. The alternative is to use a modified version of the 24-2. The Octopus has a G program, and Zeiss is working on a version of 24-2 that makes use of this work that we've published a couple of years ago, arguing that you could add 16 points to the 24-2, bring the total number to the same total number as the 10-2, so you haven't increased the time, really, for doing it, and at the same time do a much better job of detecting damage. You'll see progress, I think, in modifications of visual field test points in the next couple of years. All right, third, you want to topographically compare visual field and OCT information. And I'll say more about this in Module 7. All right. So what is the nature or pattern of glaucoma damage as seen as the OCT? So here's the Gedanken or thought experiment I want you to do with me. Suppose we didn't know about visual fields, or at least we didn't know about static automated perimetry. And we weren't biased by thinking about nasal steps and partial arcuates and categories like that. Maybe we knew about the Goldmans, we knew about arcuates in general, right? But suppose we didn't have static automated perimetry. But we did have OCT. How would we categorize the patterns of glaucomatous damage based only on OCT scans? So I'm going to give you one scheme and encourage you to think of others. I think the first thing you'd want to think about is when you look at the image. So we're going to talk about looking at these images now. If you look at the image, where is the damage? Well, the damage is here, and you can see it on the circumpapillary retinal nerve fiber layer thickness plot, which we're going to be using. Right? So that's the location of the damage. There's also damage there. Right? So in addition to location, it can vary in depth. So what do I mean by depth? Well, let's blow this up. You'll notice that this is retinal nerve fiber layer. There's almost no retinal nerve fiber layer left in this region right here. Right? Here's a second eye. This is not the same eye. Right? So that's the first eye. This is the second eye. This eye also has damage in the macular vulnerability zone, almost exactly in the same location here, right? But look now at how much retinal nerve fiber is preserved, right? All these are the same location. Preserved retinal nerve fiber layer. Compare it to the first eye, where this is very thin. So same location, but we want to take into consideration at not only location, but how much is loss, which I'm referring to the depth of the defect. Okay. Also vary in width. Once again, this damage here includes the same location we were looking at a moment ago, but now the damage probably extends from here, close to fixation, all the way to here. Right? Or from here, all the way to here someplace. And then finally, local variation. So not only does it vary where it's occurring, but how deep it's occurring and how wide it is, but also local variation. So by local variation, I mean, look at this. Nothing's left here. There's a little something there. There's more there. These are all abnormal regions. So all abnormal regions are not equal. So that corresponds to this. That corresponds to that. And this location corresponds to that. All right, let me say something about local variation. These very local variations in retinal nerve fiber layer thickness can be seen on the OCT. This is not a special OCT. This is a frequency domain or spectral domain OCT. This kind of detail has been available for 8-9 years now, right? Let's just blow up the temporal region, as we're going to look at this region between here and here. See these bright spots here? Bright spots here? Oops, sorry. These are hyperreflective regions, and they're actually due to preserved retinal nerve fiber layer axons. So you've got more axons here than you have there remaining. Now, how can I, if you don't believe me, I don't blame you. I didn't believe this at first either. But it's based upon the following study we published in 2015. In this study, we used a state-of-the-art adaptive optics SLO instrument built by Alf Dubra, and which is in Dr. Rosen's laboratory at New York Eye and Ear, and we collaborated with them on the following study. So here's the results from one patient. This is just the same temporal half of an OCT that I showed you a minute ago. This took about 2 seconds to obtain. This is an adaptive optics SLO. It's made up of numerous small 1 degree or 1 degree images. This took about 40 minutes to obtain. Right? This was processed within seconds. This took us 2 days or 3 days to process, because at least at this time, the software we had to line up each of these by hand and adjust the contrast and brightness. Adaptive optics, making use of deformable mirrors the same way astronomers use them, allows you to get a very good picture of the retinal nerve fiber bundles. So these are each of these white lines are retinal nerve fiber bundles, axons coming into the disc. Right? Now, I want you to notice that there are regions here that are healthy looking, regions that are very abnormal, healthy, essentially no retinal nerve fiber layer, no retinal nerve fiber layer. Notice that whenever there's remaining fibers, you see a bright spot. Where the fibers are missing, or the axons are missing, you see it's darker. Here, fibers missing. Fibers present, fibers missing. You are actually seeing in this OCT scan very local damage. You can see the regions of preserved retinal nerve fiber bundles. The point I'm trying to make is that there is so much more information available in OCT scans than available in summary metrics and or typical glaucoma reports. Right? And as I'll repeat later in this series of lectures, we should be looking at these images. Okay, so what's the implication for visual fields? Well, this is the most common visual field used to diagnose glaucoma. Clinicians tend to look at summary statistics, glaucoma hemifield tests, mean deviation, pattern standard deviation, including clinicians doing research, or I should say especially. Right? They also look at the pattern of results. What I'm going to be arguing is forget these. It's all about the pattern of results that you see on total deviation and pattern deviation maps. We want to look at this pattern. So what do glaucomatous defects look like on visual fields? Or what should they look like? So suppose we didn't know about visual fields. Let me go back to the question I posed. How would we categorize glaucomatous damage based upon OCT? Well, I've already argued. I'd want to know where the damage was, the location of the damage on the circumpapillary scan, the depth of the damage, the width of the damage, and something about the local variation. Based on that, what should we expect? We should expect, I should say, a wide range of patterns of visual field loss. In fact, we should expect an infinite variety that would be very difficult to categorize into discrete categories like this. And anyone who's ever tried to categorize visual fields into discrete categories will be sympathetic to this view. All right, so you want to expect a wide variety of visual field defects. Let's talk a little bit more about that. So all of these defects here in this blue region, right, are due to damage in this region here. In most cases, damage within a smaller region. Right. Whoops. Sorry. So damage here. All right, so here's your circumpapillary thickness plot, right? And this is the portion here that corresponds to this region here. All right? So let's take this and blow it up. And let's add 4 more. So now we've got 5 different eyes, all with damage in this same 90-degree region. You'll notice that in most cases the damage is going to be in about 45 degrees of that region. So again, the damage is varying in width. So here, in this case, you've got damage that goes from here to all the way over here, maybe different degrees, but it's quite wide. also quite wide here. This is less wide. There's also difference in location. So the deepest point is here on this eye, and here on that eye, right? And here on this eye. Right? So different locations, deep, and the actual depth is different. So this is quite deep here, and this is more shallow. And then finally, they vary in homogeneity of loss. If you look at the close fine structure. All right, what about visual fields? Well, you want to expect a wide variety of visual field defects, and that's exactly what you get. We can add the model here. So the model says that all of these eyes should have damage in this blue region here, which corresponds to this blue region on these scans, on this plot, and that's indeed the case. All right, so you want to expect a variety of visual field defects. In fact, I'd say continuous, right? Because all of these defects are largely due to damage in a relatively narrow region of the disc, and that damage can vary in various ways, as it just indicated. All right, let's take an example. Here's an example. Now, that doesn't fit comfortably, this defect, into this scheme. I guess you could call it extended nasal step. I'll have to tell you that this right here, at least in our experience, is probably the most common defect you can see in early glaucoma, or at least it's a very common defect. That, however, is very rare, isn't it? I mean, that almost looks like something a neuro-ophthalmologist would see. That looks like macular papillary damage, right? Well, once you look at the OCT, it's all very clear what you're seeing. This is really all one region of abnormality. So here's your model, right? That's this region here, right? Here it is on here. So you've got damage throughout this region, so you're going to expect damage throughout this region here, but it's not going to be the same. Right? So this point here corresponds to this point here, and this here, where you just have a little bit of damage left. This point here corresponds to about here, and about here where you've got more retinal nerve fiber layer left. And then if you go out here, where there's just a hint of abnormality now, you can see it there. Now you're out here, and you're over here. Okay, so that's the way we're starting to look at damage on OCT and relating to visual fields. I have one more thing, one more thing to tell you about. Here I quote from the immortal Steve Jobs. One more thing. So I want to go back to the question I posed. Suppose the OCT was developed before static automated perimetry, before the 24-2 was used, and we started with spectral domain OCT or swept source OCT, not the earlier time domain OCT combined with 24-2. I want to pose some questions for you to think about. Would we be using OCT summary metrics such as quadrant thickness to diagnose glaucoma? My answer is no. Why would we want to use this kind of a source of information when we have much more detailed information? Would many clinicians still ignore macular cube scans? Again, I say no. Would we be using the 24-2 visual field pattern in the clinic? The answer here is not a chance. Why would we be using this as the first visual field test to give a patient when we know it misses this important macular damage? If we did use static automated perimetry, and I believe we would still be using static automated perimetry, it would better sample the macula. Would there be any papers or on classifying or staging glaucoma using the 24-2 visual fields? Because almost all the staging papers in the literature, including staging used for billing, base it on the 24-2, which is underestimating at best, missing at worst macular damage. Would we be doing visual field testing before OCT scans, as some clinicians do? I don't think so. I think many clinicians are starting to do OCT scans first and then I would suggest using it to guide them in which visual field to do, a 10-2 or a 24-2. Would we be debating the use of OCT as an endpoint for clinical trials? Again, I do not think so. Finally, would our OCT reports look different? And the answer is yes, and that was the topic of earlier modules and will be the topic of the discussions in the next couple of modules. Thank you for listening, and I hope you'll return for Module 6. Thanks again.